Okay, welcome. Lauren, yes, you said you had a few more questions you would like to go over, so I've got those lined up here now. I'm going to go ahead and walk you down through these ones. I noticed that these that you're talking about these are quite a bit different than the previous ones we were working on. I mean, that's not a problem, of course. I'm just, even though it's in the same unit, what's happening for the questions that you've asked is much more geometry based, but it's kind of showing the link between some geometry topics and then the type of math that you're doing, the type of computations, I guess, that you're doing right now. But anyway, this is again going to be Math 1101A Unit 3. And we are in the book, page 147. And this is question 7. We're going to do questions. I'm going to do all the ones you asked for. That'll be 7 to 10, 12, and then number 10 on page 149. And like I said, where these are from the textbook, so these are from your notes sections, I'll go down through these in great detail. I might not do every last little bit of it, but I'll show you very thoroughly how we go about computing these ones. Now, I'll draw out a square, or I mean a roughly diamond shaped object. You remember when they had diamond, was it diamond shreddies? I think it was, because shreddies are square, right? And they were like, have diamond ones instead, and it was just the same ones, just turned. I mean, it was obviously a very tongue-in-cheek. It was consciously a joke. The ad campaign was, but it was pretty funny. I think that was shreddies, right? I don't know. I can't remember what cereal it was. Actually, I might be giving the wrong company big ups for their opponent's ad campaign. Anyway, it was brilliant. I'm just rambling while drawing out my diagram here. Don't mind me. I could have just drew the diagrams out beforehand, I suppose. A very important thing about this diagram. Now, mine is drawn a bit squish, but that's not a big deal. One reason it's not a big deal is because of those lines that I just drew. Those 4 lines there are very important. These notches on the side tell us that each of these 4 sides is the same length. That's what those notches mean. If instead we had 2 notches, say this one here had 2 notches, this had 1, this had 1, this had 1, what this means is these 3 are equal, and this one here is different. Now in this case, this one here is actually still the same, so I'll just color that over so it looks like 1 notch again. But those notches, like I said, indicate that each of these 4 sides are the same length. And if they're all 4 the same length, we know that this is a square, right? And we're also told that this is a 90-degree angle, like so. Further reinforcing that this is indeed a square. And the question tells us that it's a square as well. Okay, so there's lots of reasons why. There's plenty of reasons. It says right here, doesn't it? Look at that. Oh, you can't see my cursor. There we go. Each square. Right there. Look at that. Anyway. So all we have to do to find the side length of a square based on the area is we take the square root. Right? That's why it's called the square root. But we know that the area of a rectangle, or of a square, is length times width. Right? So the area of a rectangle is length times width. For a square, length and width are the same. So we can say that the area of a square is just going to be the side length squared, right? Because it's this side length times by itself, because we're told that all 4 of these are equal. And what operation is the opposite of square? Well, the opposite of square the opposite of something squared is something square rooted, right? We use this sign. Now, this is the same as x to the 1 over 2. Now, we will get into this we will use this a bit more later. Right now, this is kind of optional to understand, but we will definitely be using this later. And for my money, it can often be easier to use the fractional exponent for a root instead of the symbolic root. Sometimes I find it makes it clearer why the math works out to be what it is. But either way, an exponent, sorry, a square root is an exponent of a half, right? So if we have something with a square root of 2, and then we multiply it with a square root of a half, then obviously 2 times a half is 1, right? But anyway, so this is a bit of an aside here, these two. But that just shows us the way that we're going to go about answering this question. And all it's going to be is just 484. We take the square root of that. That's all we've got to do here for this answer. And now let me, I'll tell you what. I don't know what kind of calculator you've got. So instead of using my TI-84, because I'm not sure you've got one of those, I'll show it to you with just a phone calculator tipped on its side, sort of like this, right? So the button that you'll be using is this one over here. This guy right here. DASI, right there. So 484, root of 484 is 22. That one's an exact root. Anyway. So now we know that each, and it'll keep the units the same. Notice these are millimeters squared, right? So it's worth, yes, it's worth mentioning what squareds are in terms of spatial units, I suppose. So I'll do this in a different color down below, just so, to show you that this is another aside, just to show you what it means, right? Because I'm not sure which part of this was the part that you were finding a sticking point, so I'll just be very, very thorough. Okay, so say this length is 1 centimeter. I haven't measured it. It's in the ballpark of 1 centimeter. Say this is 1 centimeter here, right? And say this is 1 cm on the top, and then 1 cm along the side. This is going to be 1 cm squared. And what does that mean? Well, this is the number of dimensions, right? So this is 1 centimeter, or we could call it 1 centimeter to the power of 1. We don't write out to the power of 1, because to the power of 1 doesn't do anything, right? It's like multiplying by 1. Multiplying by 1 doesn't do anything, so we don't write it out, right? But this is 1 centimeter to the power of 1, which means this is a centimeter in 1 dimension, right? Length only has 1 dimension. Area has 2 dimensions. This is a centimeter squared, right? It's an amount of flat space that's 1 centimeter by 1 centimeter. Now, the paper, of course, is a 2-dimensional object, right? Well, sort of. I mean, paper obviously has a thickness, right? You know, the fact that books exist sort of testifies to that. But what I mean is the surface of the paper is a 2-dimensional field or representation. But I will endeavor here now to move my diagram into the 3rd dimension. So if instead we had a cube that was 1 centimeter there by 1 wide by 1 centimeter high by 1 centimeter long, this is going to be 1 centimeter cubed, right? Because it's in 3 dimensions. It's got length, width, and height. So this is a measure of volume. So this is now length, right? 1 centimeter. This is area, 1 centimeter squared. And this is volume, 1 centimeter cubed. And this is showing a little bit why we're using square root here, right? Because this is millimeters squared, because it's a measure of area. So to work backwards, we're going to take the square root. Okay, just like if it was cubed, we would take the cubed root. But anyway, you'll see a bit later on how those ones work. I'll skip going over 7b because most of what I've been saying here now has just been sort of explanation of the general concept. I think it's fairly straightforward how we go about finding the square root of something, right? You're just going to use your calculator. Once upon a time, people might have to look it up in a table, but we're well past that. And remember, once upon a time, teachers told you you'd never have a calculator in your pocket all the time. Well, guess what? Guess what you do? You do, right? It's your phone. Okay, so next up, question 8. Determine the edge length of each cube. Well, guess what? Guess what? I got a fever. No, I don't, actually. I was just about to segue into an SNL bit. Length, area, volume. We just looked at those. Area was two-dimensional, so we had to take a square root. Volume is three-dimensional, so guess what? We are going to have to take a cube root. I lied. I lied just now. You are going to have to know cube root. You're going to have to know cube root right now. My bad. It's really not anything difficult. The operation on your calculator is going to be roughly the same, just depending on your calculator, you'll have a different button to press. Now I'm going to go and draw out a diagram again here, which will take a few seconds. Giving me a few random, rambly, distractible moments. Oh, well, that's unfortunate. They really should, in order to model good good diagrams, they really should have indicated that the sides were the same length. Although they do, okay, never mind. They do say that it's a cube, right? It does say cube up here. So that's enough. Oh, crap in a basket. When I click on this, for whatever reason, I left-click to get my cursor to show up, and then left-clicking in the window causes it to go to the next page, unfortunately. Anyway, it says it's a cube right there. So if it calls it a cube, we know already that each side is the same length. I would prefer if, like the previous question, they also indicated with the notches that these are all the same, but whatever. We'll deal. Volume equals 5832 cubic inches. This textbook does alternate between metric and imperial sometimes, though I don't think you're doing any conversions in your current unit. But anyway, so we know that the volume of a rectangular prism is equal to length times width times height, like that. But here now, volume, since it's a cube means that all the sides are the same length. It's just going to be the length cubed. So it's whatever the length is, times itself again. So just like before, the opposite of x cubed is cube root of x. Now in paper, and sometimes in your assignments, you'll see it written like this. It's written just the same as the square root, just in the little crook over, of the sign. Over here, there's no number. Over here, now we put a 3 down in that little area, right? And also cube root x is the same as x to the power of a third. Okay? This will be important later on, like I mentioned. Not super important right at this moment. But now all we've got to do is cube root of 5832. Okay? So, unfortunately, this calculator, actually, yeah, good thing I'm showing you this one, because this calculator doesn't appear to have the ability to do a cube root. It's got a square root there, but I don't see the ability to define which root you're taking using that sign. So we will actually, yeah, it's good that I'm mentioning it. We will actually go ahead and use this, depending on which calculator you have. Because the thing is, not every calculator has support for writing it out this way, but you can always do it this way. So I'll show you here now. So 5832. Now we're going to go to the power of. To the power of is going to be this button here. You see this one? X to the power of y. Camera has a little bit of trouble focusing on the calculator. This one here, x to the power of y. So I'm going to click that guy, and then I'm going to do 1 over 3, and I'm going to put that in the bracket. See, so I got the number 5832 to to the power of 1 divided by 3. So we're not going to use a decimal. We're not going to do it to the power of 0.33333 or anything like that, because you always have to stop writing down your 3's at some point, which means you'll always be rounding a little bit, right? But then you notice if I do it to the power of 1 over 3, I get a nice neat 18 as my answer. Like that. Right? So the cube root of 5,832 is 18. So we know that the side length what am I doing? The side length is 18 inches. Okay, so let's see. You wanted something of question 9 and question 10 as well. So let's see. I might not do every single one of these, but let's take a look and see what this one looks like. Oh, I can't zoom in anywhere in between those two. Okay, in February 2003, Battleford's Chamber of Commerce in Saskatchewan placed a cage containing a 64 cubic foot ice cube along Yellowhead Highway. Local customers were asked to predict when the cube would melt enough for a ball above the ice cube to fall through it. What was the surface area of the cube? All right, most of that explanation wasn't necessary. All we really need, and this is going to be a fairly quick one, so I'll just cram it in down here at the bottom. This is not a particularly involved question. It's a 64 cubic foot ice cube. So the volume equals 64 feet cubed. So just like up here the volume was 5,832 inches cubed. Right, like we saw right there. Down here it's 64 feet cubed, but we're going to do the exact same thing. So cube root 64 is what we have to do to work backwards. So that's going to be 64 to the power of a third, just to show you the way that we're going to do it, depending on your calculator. And I'm going to be super lazy, and I'm going to go across with a second equal sign. Never do this. Actually, I'm not going to do that. No, I'm not going to model bad behavior. No, I'm going to go down. I'm going to go down the page like a proper math teacher. So we're going to do 64 to the power of 1 over 3, close the bracket. The answer is 4. Equals 4 feet. So 4 feet is the side length. Now that doesn't get us the surface area, now does it? What that gets us is the length of each individual side, right? So, where'd I put my protractor? Hold up. Boy, I had it a second ago, and now it's absolutely vanished. Weird. Anyway, we'll go back to defacing the value of this magic card. Don't worry, it's not a Black Lotus or nothing. Although, I mean, like I said, Faceless Butcher is worth maybe, $1, $2 maybe? I don't know. Did they give future printings of that? Anyway, it's a good card. Torment was a questionable set, though, I suppose. Though not as questionable as maybe Legions, which followed. Was the middle set of the next block. Anyway, this is some real nonsense that I'm rambling on now while I'm drawing this thing. Anyway, you are not going to be quizzed on Magic the Gathering, I'll tell you that much. 4 feet. So each of these side lengths is 4 feet. This is why I'm drawing out this cube, is to show you this is 4 feet, this is 4 feet, this is 4 feet, this is 4 feet, etc., etc. Okay? So, but you're asked to find the surface area. Well, what's the area of this first face? Well, the area of one face is going to be 4 times 4, which is going to be 16 square feet. right? This face, 4 times 4. This face, 4 times 4. This face, 4 times 4. And we know that there's 3 other ones that we're not seeing. I'm not going to do the dotted parts in the middle, although I could. I say that I'm not, and then I go do it, right? It's close. I didn't claim to be an architect. So we know that there's 6 faces on a cube like this. If the area of one face is 16 feet, well, what's the area of 6? Is going to be 6 times 16, isn't it? Right, because there's 6 faces to a cube. Just get, we know a die rolls from 1 to 6, right? A cube has 6 faces. So it's going to be 16 times 6. That's going to be 60 plus 36, which is going to be 96. 96 feet squared. Right? And it's just, once we get past this point of taking the cube root of a number, then it's stuff like just exactly like what you saw in the refresher courses. Okay, let's see. You asked for number 10, number 12, and then number 10 on the next page. All right, so we're halfway done. The cube has surface area of that. What is its volume? Okay. Make this a touch smaller here, so I get a bit more space back. This is now question 10, still in the same course. So if the cube has a surface area of 6,534 square feet. Well, just like the previous one, now I'll draw out another cube. I know this is maybe belaboring it a little bit, but it's always good to be thorough on these kind of things, because you never can tell what part might get a little bit confusing if I just talk about it instead of show it. So I'm going to err on the side of caution, and I'm going to do out a whole bunch of diagrams. Now, this is a little bit of a wonky cube, but just bear with me. So we know that the full thing, the surface area, equals 6,534 square feet. Now, like in the previous question, right, we know that there's 6 different faces to the cube, so that over here, once we found the area of one face, we had to multiply it by 6 to get the area of the full thing. So here, we want to work backwards. We want to get the area of one face now. So to get the area of one face, I'm going to divide by 6. So we're going to do 6,534 divided by 6 is going to equal, I don't know what 534 divided by 6 is off the top of my head. Although I suppose I could figure it out, because if it was 600 divided by 6, it would be 100. And this is 66 less. That's 11 less than 100, so that'd be 89. So that should be, this should be 1,089. 6,534 divided by 6, 1,089. Look, would you look at that? Would you look at that? Look at that. I figured it out very slowly in my head, then even more slowly on calculator. All right, so it's 1084 feet squared is the area of each of the faces. Now we've got a question like we had back in 7, where we've got an area that we know, but we know it's a cube, so we know each side is the same length. So we have a question just like this, so we just need to take the square root of it. All right, and let me just, yes, I should indicate on here that this is indeed a cube. All faces the same length. All sides the same length, sorry. I mean, the faces are the same length too, and then the same area as well. So what I'm going to do is square root of 1089 is going to equal, see, a square root of 1089, 33. 33 feet. Now it goes, it's not feet squared anymore, now it's feet, because the square root, like I said, the square root, or any operation, affects the unit as well as affecting the number. So we took the square root of the number, and at the same time we take the square root of the unit as well. And it is worth noting that this is positive or negative 33, but because we are dealing with a geometry problem, we know that it's a positive answer because, you know, in the real world, a negative length kind of doesn't really make sense. I mean, it makes sense sometimes in small circumstances, like cutting something apart, you could consider it to be subtracting length. But, like, you couldn't look at a block and be like, that block has a length of -4 feet, right? It doesn't make any sense. Anyway, that's more of a physics lesson, actually, because then it's, you know, is it a vector or is it a scalar kind of thing, you know? Anyway, I don't need to bog you down with stuff that you're not doing yet. So, each of the side lengths is 33. I think this is fairly straightforward. So, what is its volume? Well, the volume of a cube with side length 33. Remember, volume of a rectangular prism is length times width times height. And here all three of them are the same because it's a cube. So we know that it's just going to be length cubed. So it's going to be 33 to the power of 3, which is going to be 3 33s times together. You need to go back to the old phone. 33, and we're going to raise that to the power of 3. There we go. It's going to be 35,937 cubic feet. So quite a large object, for sure. But I mean, you know, as soon as we know that each side is 33 feet, right? 11 meters on each side, practically. It's a big chunker. Big chungus. I don't say memes to try to be cool. I am perfectly content with being uncool. I say memes because I'm an idiot. Not really. Anyway. Yes. Large chungus. So we're going on to 12a, I believe. Determine the perfect square whole numbers and the perfect cube whole numbers between each pair of numbers. Well, determine's an odd word to use there. Because we're not really gonna, I guess we could determine them, I suppose. Yeah, let's play it the way they say it. Let's determine them. Perfect square whole numbers and perfect cube whole numbers between each pair of numbers. So let's just try some. Let's take some numbers and then square them and see where we end up, right? Now, we're not just going to go through each number and square root them or anything like that. I'm just going to start taking whole numbers and start squaring it and see where we get. Now, we probably know 10 times 10 is 100, right? That one's pretty straightforward. That's easy. So we know that 100 is a lot smaller, so we got to try a number bigger than 10. All right, let's try 20. Well, it's 20 times 20. That's 400, right? That was pretty easy because 2 times 2 is 4, right? So 400 is too big. All right, so we know, because that's past 390. So we know already that we're greater than 10, less than 20. Okay, 15. 15 squared, I know, is 225. Right? We can do them on the calculator as well. You can also look them up in a table. Right? This is not like a terribly important question, to be perfectly honest, because your textbook, I think your textbook even has it in a table near the back. I believe the square and cube numbers up to something or another are listed. But either way, I mean, you can find them online, or your calculator knows all of them. You just got to tease it out to find it out. Anyway, 15 squared, like I said, is 225. That one's too small. But we already know 20 squared is too big, so we haven't got many left to check. So let's check 16 squared, 256. That's a very important number in computing. That's 16-bit. But anyway, so 16 doesn't work. That was too small. 17 squared, 289, also too small. 18 squared, 324, that one fits. All right, so 18 squared equals 324. That's all we're doing. 19 squared, 361. Okay, so we're done with the squareds because we know now that 20 is too far. That was too big. Now I'm going to do the cube numbers, and we're going to do the same kind of thing. Well, what's 10 to the power of 3? That's 1,000. Well, that's way bigger than 390. All right, so let's dial it back a whole bunch. Let's try 5. 5 to the power of 3. 125, that was too small. Okay, so let's try maybe 7. 7 to the power of 3. 343, there we go. All right, so 7 to the 3 equals 343. Good. Okay. Let's see if any more of these fit. 6 to the 3? Nope, too small. 8 to the 3? Way too big. 512. All right, so now we're done. Okay, we're only going to take whole numbers squared because that's why it says perfect square whole numbers and perfect cube whole numbers. Because if we went into decimals, of course, there's an infinite number of square numbers between any two other numbers if you're allowed to use as many decimal places as you want. But we don't, so don't worry about that. We're just going to be checking whole numbers, and like I said, there's not very many of them in any given intervals. All right, and this question is not, like I said, it's not terribly important of one. I'll just do D here really quickly. The easier way to do it, honestly, like you could do it trial and error like this. Honestly, this was a bit of a ham-fisted way to do it. The easiest way to do it is going to be to take 1,200, your lower bound, and take the square root of your lower bound, like so. Right? So I'm going to actually show you two different ways of doing this. So the lower bound, square root of your lower bound, is 34.6. And what's the square root of your upper bound? 1350. It's going to be 36.7. So we know that in between these, what whole numbers do we have? 35 and 36. Right, because we're only taking the whole numbers. So 34 is out because this is bigger than 34. 37 is out because this is less than 37. So it's only going to be the numbers 35 and 36. That's it. All right, that was considerably quicker than doing it this way. And the same deal. I'm going to do the cube root of 1,200 now, which is going to be 1,200 to the 1 over 3. Right, just to show you how to do it in a way that, some calculators will have a button for this. Some calculators will have a button that looks kind of like this. Some calculators will have that button, and you can use that one. I don't know what calculator you're working with, so generally if I don't know, I'll show based on the phone calculator, because this is one that people usually have access to. And of course you can get, there's loads of different phone calculators. You can download loads and loads and loads of different apps with staggering amount of variation and different degrees of sophistication. But this is just the basic. All right, so I'm going to raise it to the power of 1 over 3, like I said, and then we end up with 10.6. Now if I do the cube root of 1350, right, that's going to be 1350 to the power of 1 over 3. D to the power of 1 over 3, like so. We get 11.0. I'll call that 11.1, yes. So I'm rounding to 1 decimal place. So the only number in between then is going to be 11. Okay, so we have 35 squared and 36 squared, and we have 11 cubed as the ones that are in this interval. So not terribly difficult questions, I wouldn't say. But, you know, like I said, I don't necessarily like to say, oh, well, this is not difficult, because it seems to imply that, you know, people should be able to understand it right away. You need, you know, people will always need explanation for things the first time, for sure. Right? And it is, like I said, it's way harder to understand math from reading a paragraph than it is to understand math from seeing somebody actually do the work. And now I believe the last one you asked about was question 10 over here. So let me zoom in. The program's a small bit frustrating. Don't mind me. I'll get there. I'll get there eventually. That's the important part. Right? That's my catchphrase. We'll get there eventually. Okay. There we go. Look at that. Fits in there nice and good. All right. You get to see how the sausage is made in real time here. I can show you a shot of my OBS window to see all the Frankenstein monster that is my scenes and source menu. Anyway. And it is Frankenstein's monster, by the way. Not Frankenstein. All right, I love that book. I teach that book every chance I get. All right, that's a great book. Okay, so a cube has a volume of 2,197 cubic meters. The surface is to be painted. Each can of paint covers about 40 square meters. How many cans of paint are needed? Okay, this is a great question for you to have asked about, Lauren, because this is very similar to questions you will see on your test. I'll tell you right now, you're pretty much guaranteed to see a question that is structured like this one. And if not on this test, then on other ones as well. Because, you know, paint covering area, oh boy, what a great math teacher chestnut that one is. That's a real good standby. Yeah, I love painting. Yeah, of course. It's like, it's not easy. It's not. Anyway, no. I was thinking of a different joke, but you know what? It's time to, I'll bail on that one. So a cube has a volume of 2,197 meters squared. So the volume, 2,197 meters cubed. Sorry, I might have said squared just then. The surface needs to be painted. So this is now very similar to this question, to question 9. Question 9 back that we looked at earlier. This is extremely similar to this because we're just gonna get this exact same sort of answer that we got back here, and then once we get to there, there's one small other step to do. But then, again, I'll draw out a cube just because I feel that it's useful to have a diagram. Okay, and it is a cube, we were told, which means that all of these are indeed the same length. Like so. So if we want to find one side length, all we're going to do, cube root of 2,197, which equals 2,197 to the power of a third, which is going to be, I'm going to boot up my phone again, 2,197 to the power of 1 over 3, close that bracket, and that's going to be 13 meters. So what this tells us is each side length is 13 meters. So if each side length is 13 meters, what's the area? The surface area. Surface area is going to be 6 times 13 squared. Right? I'm cutting to the chase a little bit here compared to what I did in question 9. Because in question 9, the way I phrased it was area of one face is 4 times 4 is 16. Area of 6 faces was then 16 times 6. Here I'm just doing it together, right? Because each side length is 13. 13 squared is going to be the area of one face. And then that number, 169, times 6 is going to be the surface area of the total. Right? So it's going to be 6 times, and like I said, 13 squared is 169. I'll do it on here as well just to show you. All right, so 6 times 70 would be 420. Nice. But it's 6 times 69, even nicer. Stupid Reddit jokes. All right? No, these are dumb. These are dumb jokes. But it's going to be 420 minus 6. So that's going to be 414 plus 600. So it should be 1,014. Yes, look at that. We did it. 1,014. Don't worry, just the mental arithmetic thing is something that I got used to teaching before, because that was a big part of the curriculum when I taught in high schools. And it's just something you get used to modeling, right? Just to explain how, different ways of going through the mental math. But anyway, it's totally optional for our program because you'll have a calculator for literally all of it. Right, so it's going to be, and that is meters squared now, because when this was 13 meters. When those meters squared, they became square meters. So that now is the total surface area of the full cube. Now, we know that each can of paint covers 40. So, if there's 1,000 and change square meters to paint, each can covers 40, you're going to need, I believe the proper term is a shitload. You're going to need all right, I'm not supposed to swear on school stuff. No. Don't tell anybody. Don't tell anybody. I don't know what that word means. Divide by 40 meters squared. So we're just going to divide that by 40. That's going to be 25.35. And of course, since we're talking about how many cans of paint he needs, or the person, or are needed, never mind, it wasn't even told to have a person. We're going to need to go up, right? Because if you could say 25.35. If you said that on a test, I wouldn't mark you wrong. But 26 cans. We'll say 26 cans are needed because if you bought 25 cans of paint, you'd be pretty sad when you got right to the end and there was a tiny little bit left that you weren't able to paint. Right, so 26 is the number that's needed. Okay, and that is all the questions that you asked me to go through. Hopefully that makes a little bit more sense there now. It does kind of link up with the stuff that you've been doing so far in the sense that this is showing you, these exponents on the variables, kind of what those actually translate into. And as far as I'm concerned, the best way to view them, especially for the exponents of 2 and 3, is to think of it as the number of dimensions of the unit. Right? Perhaps this is just showing sort of the way that I learned this math, but I find that thinking of it in sort of physical terms tends to make a lot more sense a lot of the time. So if we think of to the power of 1 as 1 dimension, so just length, right? To the power of 2 is 2 dimensions, so length and width, or it's a measure of area, like how much flat space something takes up. And then if it's 3, it's length, width, and height, so it's how much like real three-dimensional space something takes up. Then to the power of 4, I guess it would count how much time it takes up as well. But anyway, no, we have 3 spatial dimensions, and that's just, right? That's just all we've got, like I mentioned, until Walter. Yes, Walter. Walter is the name of the doctor from Fringe, right? Until Walter finds a way to send us to a parallel universe with more than 3 spatial dimensions. Until that point, we're stuck. We're stuck with just a physical analogy for squared and cubed. But anyway, hopefully that explains a little bit of what you were asking about. Yeah, let me know if you have any more questions. And I hope that was helpful.